The next statistics video is about confidence intervals and student t-tests. After watching this video, you should be able to identify the appropriate t-test case, depending on what kind of data set you're given, and correctly apply the t-test to determine if the mean of two data sets are significantly different. A confidence interval is essentially a measure of how confident you are you know the correct answer. If you know the correct answer, then you don't need a confidence interval, but the larger the confidence interval that you recommend, the more likely it is that the right answer will be in that range. Confidence intervals are calculated using the mean and standard deviation of an n number of measurements. Then you can say, with a 50 or 95% confidence, that the right answer lies within the calculated range. Shown in this figure is both the 50% and 90% confidence interval that the mean will lie in this range, with the center being the true mean. So you can see that the 50% confidence interval is much smaller than the 95% confidence interval. This is a really important point to remember about confidence intervals. The larger the confidence interval, the larger the range, and the more likely it is that whatever true answer you're looking for will lie within it. One common application of confidence intervals is student's t-test, which statistically compares means using confidence intervals. The student's t-test was initially published in 1908 in Biometrica. Student was a pseudonym for an employee of the Guinness Brewing Company in Ireland, who was allowed to publish under a pseudonym because Guinness restricted his publications for proprietary reasons.
But essentially, if we want to be 95% confident that the true mean lies within the confidence interval, we use this equation. And one thing I do want to point out is that n here is the number of measurements, and t here is the degrees of freedom. And you look t up for the degrees of freedom, which is n minus 1, not for n. So if you have 5 measurements, you're going to be looking for the t for the degrees of freedom equal to 4.
The student's t-test can be used to statistically compare means in several different applications. So we're going to call these cases. So case 1 is where you're comparing your data against a true value, such as a NIST standard. Case 2 is comparing replicate measurements of the same sample measured with different techniques, like if you wanted to measure arsenic in soils by X-ray fluorescence and by dissolution and then ICP-MS. Case 3 is where you would be comparing individual measurements of many samples measured using 2 different methods, but you only measure each sample one time by each method. An example of this is if you had 300 water samples and you wanted to measure nitrate in all of them by 2 different methods, you might only have enough money to measure each sample one time. Let's look at an example of each case. Remember, case 1 is where you're comparing your data against a true value.
Number 1, comparing your measurements with the standard. You're going to use the same equation, x bar plus or minus ts over the square root of n. So the example in your book, we're just going to go over the example in your book where you have a NIST standard that's 3.19% sulfur, weight percent sulfur. Your data you come up with is 3.26 plus or minus 0.06, which gives you a range of 195 to I said that totally wrong. 3.195 to 3.325. And so if the range of your data includes the known value, there is no statistical difference. However, you can see that the lower limit is actually a little bit higher than what the NIST standard is, and so actually this is because the NIST standard value does not lie within the range of your data. There is a statistical difference, and you need to go back to the drawing board and figure out how to make your method more precise or more accurate, but in this case more accurate.
Now let's move on to case 2, where you're comparing replicate measurements of the same sample measured with different techniques.
So here's the second one, where we're comparing replicate measurements of the same sample using 2 different methods. So here you're going to calculate a t-value, and then you're going to compare it to the t-value that you would find in the table for your desired confidence interval. So you just do mean 1 minus mean 2 over S pooled times the square root of n1 times n2 over n1 plus n.
And last but not least, case 3, comparing individual measurements of many samples measured by 2 different methods, but with each sample only being measured one time by each technique.
So the third example that we're going to look at today is comparing individual measurements made using the 2 different methods on many samples. So say you have a ton of water samples that you want to get analyzed and you only have a finite budget. And this type of stuff happens all the time. Well, this is a method for being able to analyze each sample via 2 different methods only one time, so no replicate samples, or no replicate measurements. And you're going to try to figure out if method 1 or method 2 is better, or if they're significantly different. So, you calculate your standard deviation for the difference. Your book actually has a great illustration of this, but basically you take each measurement minus each measurement x1 minus x2, so method 1, method 2, and then that gives you the difference. So then you take each of the differences minus the the mean of the differences. So you add up all these differences and get a mean, and then you square them and then divide it by n minus 1 square root to get your standard deviation of the differences. All right, then you calculate t-calc by the same thing, the absolute value of the mean of the differences divided by the standard deviation of the differences times the square root of n. So if the t-calc is greater than the t-table, there's no significant difference. And we'll do you'll have plenty of opportunity to practice figuring out which test to use, and also practice using these equations.
As a few final thoughts, I would just like to say that the 95% confidence interval can change depending on the number of measurements that you're basing it on. So you can see here the 95% confidence interval for 5 measurements is much broader, much wider than the 95% confidence interval for 21 measurements. The other thing that I think it's important to point out is that there's several ways that you can report your error associated with the measurement. You can report a standard deviation, you can report a confidence interval based on a variable number of measurements, but it's really important to identify what error you're reporting when you're reporting your data.